Today we will be talking about solid-solid mixing. To help you frame the flow of discussion, here is a brief outline. To begin the topic, we will go through a few introductory points about how it is used in industries, as well as different types of solid-solid mixing.
Then we will discuss a specific type of solid-solid mixing called binary component mixing and how it will help understand the mechanisms of mixing.
Finally, when mixing a specific type of solids called cohesive powders, some considerations need to be taken to adapt to its special properties. Also, in between each section, we will introduce different types of equipment that are used in solid-solid mixing operations that you may encounter in the future. Let's begin with part 1.
For the first section of this discussion, we will go through introductory concepts about solid-solid mixing and the mechanisms involved during the process. Also, a phenomenon called segregation happens, which we will discuss later. You may already be familiar with the concept of mixing. The common treatment refers to the mixing of two liquids, as seen here, or the suspension of solids in a fluid, as in this one. This is often done by subdivision and blending of separate fluids so that microscopic diffusion will lead to homogeneity. However, mixing can also apply to solids. Solid-solid mixing is a unit operation widely used in manufacturing, in which two or more solids are treated so that each solid particle lies as nearly as possible in contact with a solid particle of each of the other ingredients. This is a process that tends to result from a randomization of dissimilar particles within a system. Notably, solid-solid mixing is different since compared to fluids, mass transfer is more difficult since flow is not accomplished in the same way. A discussion of the details of mixing cannot proceed without its rationale. It can be expressed in many ways, but the rationale is the same. You see, the mixing of solid particles is an essential process to create a homogeneous distribution of solid particles in situations where two or more types of solids are combined. This is important in cases where an active ingredient needs to be dispersed over significantly larger volume, and thus the concentration of the solid raw materials needs to be distributed evenly over the entire volume. You see, the goal of mixing is to neutralize any fluctuations in this concentration. This example is most applicable to the pharmaceutical industry, where the active ingredient such as the vitamin or medication, in cases where it is a solid compound, is usually only a portion of the tablet that is actually ingested. A portion of the tablet mass is composed of fillers that make it easier for the drug to be handled as a tablet compared to a few crystals of the pure active ingredient. Not to mention the host of other components such as anti-adherents, binders, coatings, disintegrants, lubricants, preservatives, and colors that are also added for specific roles in the tablet. All these components have to be uniform across the tablet to ensure that the drugs are efficiently delivered, or in cases where only a portion of the dosage is required, the drug can be portioned and still be effective. So, how do we describe what happens when all these solid components are mixed? There are three accepted mechanisms for how solids are mixed. We have dispersion, convection, and shear. Since we have already illustrated the case of singular particles, let's begin with diffusive mixing. Also called dispersion or micromixing, this type occurs when individual particles within a powder bed move randomly, which causes them to change their relative position in relation to one another. Since this mechanism deals with individual particles, the effect is more localized, hence the term micromixing. This means that dispersion is evident as well-mixed portions of the entire volume. Hypothetically, if only diffusive mixing is present in the case where two solids are initially separated, the mixing will take a very long time, since there is a very low number of assorted neighbors in the bulk white or bulk black regions. Dispersion still happens, but the neighboring particles are of the same type. So for diffusive mixing in the areas shown in figure A, white will still replace white, and black will still replace black. In this figure, diffusive mixing where white and black particles can interchange can only happen at the interface, slowly spreading away from this initial surface. This will take quite a long time for a very large volume. This is where the second mechanism, convective mixing, comes in. Convective mixing, also called bulk transport or macromixing, takes place by transferring the part of material from one location to another location in the system by means of blades or paddles of the equipment. This means that particle groups, not individual particles, are moved from one position to another. Earlier, we said that dispersion is difficult as a lone mechanism because for an initial state of spatially separated volumes, the probability of assorted neighbors is too low at areas away from the interface. Well, convection increases the number of assorted neighbors of a single particle by virtue of its bulk transfer, thus making dispersion a more effective co-mechanism. A third mechanism is often referred to in some sources. In shear mixing, shear stresses give rise to slip zones, and mixing takes place by interchange of particles between layers within the zone. We can see in figures A and B that the action of the mixer induces velocity gradients within the powder bed, which causes the top layer to shift. We can also say that the application of the shear force creates an unstable shear slip plane, which causes the powder bed to collapse. This collapse causes a rearrangement of the particles, as seen in figure C, which leads to mixing. These mechanisms, dispersion, convection, and shear, show up in the operation depending on the kind of mixer being used. The mechanisms previously discussed talk about how mixing happens, but how do we evaluate how successful the mixing process was? Well, the efficiency of mixing is dependent on, first, the materials being mixed. Specifically, the properties such as particle size distribution, density, and surface roughness. Different properties indicate different operating parameters that must be used in order to successfully mix solids. For example, larger particles would logically require less effort to mix due to the decreased variability of the particles. Second, the process and equipment used. The design and operation of the mixing unit is also important. Parameters such as mixing time, dimensions of the impeller, the size of the mixer, etc. are all determinable variables that affect the mixing process. Third, the intermediate operations. While the mixing itself is the core process, methods of feeding, sifting, weighing, and transport may undermine the attempts to make mixing efficient. It is not enough that the mixing process itself is optimized, but the surrounding operations should also maintain the standards set by the core process. On the other hand, there are also consequences when mixing is not performed properly. First, overmixing. Too long of a residence time in the mixer can also cause strain on the mixture, which may affect sensitive products, especially in batch operation. This overmixing results in attrition, or the creation of fine particles due to friction. Heating of the volume may also happen, which is a concern for heat-sensitive solids. Poor product, which may be off the desired specifications, may result in product loss, or time lost due to remixing, which is also costly. For example, remixing means having to reuse equipment, which means that instead of 10 batches, the shift can only produce 9 batches. That's one batch short of the quota. Effects of poor mixing may be apparent if mixing occurs as the final operation, but mixing is usually an intermediate operation. As such, its effects on the final product may not be observed until the end. Now, we mentioned that intermediate operations can affect the success of mixing. For the most part, downstream processing, compared to feed preparation, may destroy the product quality more due to a phenomenon called segregation. We can treat segregation as the opposite of mixing, or just see it as a divergence from the desired homogeneity of the product. It is important to know how segregation manifests. If mixtures are unsuitably stored or transported, they will separate according to particle size, hence segregation. There are about 13 or so recognized segregation mechanisms and can be categorized based on similarities, while some are just special cases of one mechanism. The categories we have chosen present segregation based on the size of the segregated particle. We have trajectory, sieving, fluidization, and agglomeration. First, trajectory segregation. It is also called transport segregation and is a class of side-to-side segregation. This occurs in large particles. When large particles are in flight or free fall or have relatively high rolling or moving velocity, such as during heat flow or shoe flow, trajectory segregation happens. It often manifests in a container, where the small particles will end up in the center, surrounded by the larger particles. Next, sieving segregation, also called percolation segregation, and is a class of top-to-bottom segregation. This occurs in small particles when they move through void spaces formed by large particles due to external energy input such as vibration and shear motion. This type of top-to-bottom segregation results where the coarse particles are situated at the top and the fine particles at the bottom. Next, fluidization segregation. This is also a type of top-to-bottom segregation, much like sieving segregation. This occurs in fine particles. It manifests when fine particles appear in the mixture and/or free-fall height exists, such as in pneumatic conveying. This type of top-to-bottom segregation occurs where the fine particles end up at the top and the coarse particles at the bottom, which is the reverse of sieving segregation. And fourth, agglomeration segregation. This occurs in cohesive fine particles. This occurs when fine particles are subject to moisture reabsorption, which largely contributes to cohesion. It manifests when one of the components prefers to self-agglomerate or attach to particles of the same material when brought into close contact. More about this topic will be presented later on. For my turn of introducing equipment, we will talk about 3 pieces of equipment designed to primarily operate using diffusive mixing. These mixers typically operate by tumbling motion, since diffusive mixing operates by the creation of a fresh interface where the particles are introduced and interchanged. First, the double cone blender. The double cone blender consists of a double cone on a rotating shaft and is usually used for small amounts of powders. As mentioned, mixing occurs due to the tumbling motion of the container. Because of this setup, the double cone blender is efficient for mixing powders of different densities. Next, the IBC blender. IBC stands for Intermediate Bulk Container and operates by using an irregular container clamped to a rotating arm that induces the mixing. This container can be removed from the mixer, so it can be charged or discharged away from the mixer. This is ideal for multi-product environments, so different containers can be used for each type of product, therefore saving time. The V-blender. The V-blender is made of 2 hollow cylindrical shells joined at an angle of 75 to 90 degrees. The blender container is mounted on trunnions to allow it to tumble to allow mixing. That ends part 1.
We've talked about the mechanisms involved in the mixing of solids. This time, we will illustrate the results of the mixing and how it is evaluated visually or by calculations. Binary component mixing is a method in which 2 solid materials, Hence, binary and particulate form are dispersely mixed to achieve a specific distribution. So since solids have low flowability, imperfect mixing happens with a degree of randomness. This variation in composition resulting from mixing can be described using, first, standard deviation, in which it is a statistic that measures the dispersion of a data set relative to its mean, and second, the most commonly used is the variance, which is a measurement of the spread between numbers in a data set. The mathematical description of a mixing process starts by considering the simple case of mixing two components differing only by color, red and blue in this case. So two colors of beads go through stages of mixing, where we can see how the variance changes as mixing proceeds. The overall proportion of blue chips is 0.472, and at any instance in time, if we were to split the mixture into many different samples and investigate the proportion of blue chips within the sample, we would expect to obtain a proportion of still 0.472. However, it is unrealistic to expect that all samples to have this proportion of blue chips. Some samples will have more and some may have less. But the overall mean average of blue chips as a proportion must be equal to the value of 0.472. We can prove this by taking samples from the fully mixed mixture as shown in the bottom figure. The illustrated figure has such a collection of samples. The tallying of these red and blue chips can be tabulated as seen here, where there are 21 separate samples. So the lowest proportion, as you can see, of blue chips is 0.1 and the highest is 0.78. And as mentioned earlier, if we were to split the mixture into many different samples, and if we investigate the proportion of blue chips within the sample, we would expect to obtain a proportion of 0.472. To illustrate the constant proportion, here is a comparison of the calculations performed to get the average proportion of blue chips. So the tabulated results from the 21 samples gave us 0.472, while the fraction of blue chips in the unmixed sample is also 0.472. Since the mean portion of the blue chips has been calculated, the variation in composition can be quantified using the following equations. So the mean proportion calculated over all the samples is 0.472, the same as the overall proportion used. So to calculate for the standard deviation manually, we expand the summation operator for all 21 samples in the numerator divided by the number of samples. Taking the square root gives us the standard deviation of 0.195. So next, to calculate for the variance, it is just simply the square of the standard deviation, which is then equal to 0.0382. So if these samples were to be sold as our product, then the variance between the products would be an important measure of the difference in quality of our product. For sample homogeneity, the uniform mosaic figure on the left illustrates an ordered dispersion of particles, rather than a random dispersion as seen on the right. So this uniform mosaic might be the degree of mixing desired, but it is very unlikely that it will be achieved by random mixing. It can only be achieved by placing the particles in order and not by mechanical mixing process. In 1943, Lacey provided that the variance of a binary mixture is sigma r squared is equal to pq over n sub o, while the variance for the worst case expected in a binary mixture is simply sigma O squared is equal to PQ, where P is the proportion of component 1, Q is the proportion of component 2, and N sub O is the number of particles. However, these expressions are only good for discrete systems, such as in the example case dealing with a finite number of red and blue chips. You may recall our example as being measured by number of particles and not mass, which is not the case for industries where we deal with tons of material. On the scale of industrial mixing, where powders cannot practically be referred to by the number of particles because of the sheer volume, this expression for variance need to be revised in order to consider the mass of the powder instead. This rework was done by Stange in 1954 by considering the mass of the sample, the mass fractions of the components, mean mass number of particles of the two components, and the standard deviation of the distribution. However, the mean mass by number of particles is still applicable to discrete systems, so we need to improve the equation once more. So if we assume spherical particles and a homogeneous solid density as done by Poole and Taylor in 1964, we can simplify the equation further. Note the difference in the variables of capital W as mean mass by weight compared to small caps W, which is the mean mass by number. Now let us take a look at the sample problem. So according to British Pharmacopoeia standard, the allowable variation in composition of an active ingredient is plus and minus 10%. A tablet contains 10% active ingredient and 90% inert diluent. Assuming that all particles are all the same size and the particles are size distributed so that the mean weight of the particle of active ingredient is 300 micrograms and the under ingredient is 100 micrograms. Calculate for A, the minimum number of particles to each tablet, and letter B, the mass of the sample or tablet taken. So for this problem, we are given with the variance for the binary mixture, which is equal to 0.10. And we are also given with the proportion of two components, which P is equal to 0.1 for our active ingredients. Q is equal to 0.9 for our inert diluent. So we are also given with our mean masses by number of particles in the two components, which are 300 micrograms for the active ingredient and 100 micrograms for our inert diluent. So to solve for letter A, for the minimum number of particles to each tablet, we use the variance for binary mixture equation, which is sigma r squared is equal to pq over n sub o. So we are looking for the value of our n sub o, which is the number of particles. So with this equation, we plugged in the given, and then we got the value of our n sub o is equal to 0.9 number of particles. So to solve for letter B, which is the mass of sample taken, we use the variance equation by Poole and Taylor, in which what we first did here is that we calculate for our n sub p and our n sub q, in which is the total number of particles for the two components. So we did that by multiplying our n sub o, our number of particles, with the proportion of each component. So with that, we got a value of our n sub p, which is equal to 0.09 number of particles for our active ingredients, and our n sub q is equal to 0.81 number of particles for the other ingredients. So since we are given with the mean masses by number of particles of the two components, we use that to convert our small letters p and q, which is our proportion of two components, to big letters p and q, which is the mass fraction. So what we first did here is that we calculated for the mass of p and q by multiplying the mean masses by number of particles with its number of particles for each ingredient. So we got the value of our mass of P, which is equal to 27 micrograms, and our mass of Q, which is equal to 81 micrograms. So since we already have our mass of P and Q, we then use that to calculate for our mass fraction. So our P is then equal to 0.25 and our Q is equal to 0.75. So with these values, we plugged it into to the variance equation by Poole and Taylor. So we got the mass of the sample, or the mass of the sample taken, which is equal to 468.75 micrograms. For my turn of introducing equipment, we will talk about three pieces of equipment designed to primarily operate using convective mixing. So our first equipment is a ribbon blender. The ribbon blender uses agitator that mixes material in a trough. The agitator is shaped similar to a rotating ribbon, hence the name. They are mostly used for the addition of small amounts to larger components, but it is very difficult to clean. An equilibrium state of mixing can be achieved when using the ribbon blender. Next equipment is a paddle blender. The paddle blender consists of a U-shaped horizontal trough and a fabricated paddle agitator. The paddle agitator includes multiple paddles positioned to move materials in opposing lateral directions and radially. The third equipment is the plow mixer. The plow mixer projects and hurls material away from the wall into free space in a crisscross direction and inversely back again. The plow separates and lifts the product in a three-dimensional motion, while the number and arrangement of the tools ensure agitation back and forth along the length of the vessel. So that ends part 2 of the discussion.
For the third part of the discussion, we will be talking about a specific type of solid referred to as cohesive powders. We will talk about what they are, what causes the peculiar properties, and how they are dealt with. Derek Geldart provided a convenient criteria for predicting the fluidization behavior based on the Sauter mean particle size and the particle density. Basically, the classical Geldart's diagram summarizes empirical observations on beds fluidized by dry air at ambient conditions in terms of particle size versus the relative density difference between the solid particles and the gas. The chart is the result of these experiments. The particles are classified into 4 groups. Geldart groups A, B, C, and D as depicted in the figure shown. In this section of the report, we will be focusing more on Geldart group C. Group C powders are the very fine cohesive powders that are incapable of fluidization in a strict sense. The interparticle forces in these powders are large compared to the inertial forces on the particles. As a result, the particles are unable to achieve the separation they require to be totally supported by the drag and buoyancy forces, and true fluidization does not occur. Geldart group C powders contain self-loving particles and tend to stick together and don't segregate. They are typically less than 30 micrometer. The typical flow of a non-cohesive or free-flowing and cohesive powder in a rotating drum is shown by the figure. The non-cohesive powder gives a regular flow with a low value of the flowing angle as seen from figure 1a, or granular sugar, while the flow of the cohesive powder is irregular with a higher average flowing angle seen from figure 1b, or powdered sugar. Examples of cohesive powders include face powder, flour, fine silica, talc, and starch. More examples of cohesive powders can be seen here. These powders are all ingredients for tablet making. Here we can see that powder A, C, and D all behave similarly. They are more granular or have relatively large particle sizes, they have a relatively low peak, and they form a conical heap. This translates to ease in conveying. On the other hand, powders B and E look light and fluffy, have a high peak, and form an irregular heap. These cohesive powders behave differently as a heap and definitely when being conveyed and mixed. So why do they behave this way? The interparticle forces generated by electrostatic charging, van der Waals forces, and forces due to moisture are the reason for particles to stick together, preventing segregation as the particles are not free to move relative to one another. We will go through each of them. The weakest attractive forces are usually van der Waals forces. Fluctuating polarizations among nearby molecules and particle surfaces trigger these forces. Van der Waals forces increase proportionally to the square of the distance between two particle centers, meaning that even very small particles may become extremely cohesive. Van der Waals forces are the reason why granular sugar can be very free-flowing, but finely ground confectioner's sugar can be very cohesive. Electrostatic charging, on the other hand, can be a mildly strong attractive force that helps to form a cohesive structure. As electrons are exchanged between two surfaces that come into contact or brush against each other, this happens. This rubbing may occur between particles or between a particle and its surroundings. The strong unified bonding between particles is due to the positive to negative attraction. Lastly, forces due to moisture is influenced by adhesion forces caused by the overlapping of the adsorbed layers of neighboring particles, thus it requires contact between particles. Formation of liquid bridges between particles exerting an attractive force between particles can also cause cohesion due to moisture. This moisture bonding is also the primary reason for agglomeration segregation that was previously shown in Part 1. Cohesive powders don't disperse easily with other particles and form clumps. To break these clumps and get the particles to mix intimately with other particles, high mixing energy and shear is required as these have the tendency to restructure in clumps. The figures illustrate the different types of blends containing both cohesive and free-flowing ingredients. The first figure illustrates a poor blend containing all cohesive ingredients. The next figure shows a poorly mixed blend where one cohesive ingredient's particles are still clumped together because of their self-loving bonds. The last figure shows a blend where the cohesive particles have been properly separated, then allowed to form bonds with the other particles in the blend. To deal with some cohesive powders, mixers with impaction mechanisms, which rely on a bulk circulation of powders, can be used to apply a small portion of a fine cohesive powder to a free-flowing bulk material. This is called the coating process, where fine particles can preferentially bind to coarser or parent particles, resulting in a high-quality mixture. Or, as mentioned, a mixer capable of imparting shear is required to break down the cohesive bonds between particles and thoroughly mix them into a blend. The amount of shear imparted by the mixture must also be matched to the cohesive strength of the particles. Shear mixers that can be used for cohesive mixtures are available. To illustrate dealing with cohesive powders in process, this variant cannot be properly sieved due to the cohesive behavior of the material. As an example of the processing of shear equipment being used to deal with cohesive powders, this mixer uses intense rotating action together with a wall attachment that further impacts shear action to the cohesive mixture. For my turn of introducing equipment and the last three equipments we will discuss, we will talk about three pieces of equipment designed to primarily operate using shear mixing. In a planetary mixer, the mechanism of mixing is shear applied between moving blade and stationary wall. Mixing arm moves around its own axis and around the central axis so that it reaches every spot of the vessel. The sigma blade mixer consists of two contra-rotating blades that is ideal for dough. Intermeshing of sigma blades create high shear and kneading action. Its power consumption is high and also difficult to clean. And finally, the runner mill consists of one or two heavy steel or granite rollers mounted on a horizontal shaft and turned round a central vertical shaft on a bed of steel or granite. It is used to crush aggregates and mix it well, but it is also used for very cohesive mixtures. So that ends our report on solid-solid mixing, including some notes on cohesive powders. Thank you for listening.